o'clock at night, so I hope that I don't sound too sleepy. And I'd like to thank Leonardo Energy and the DSM University for giving me this opportunity to present the results of this project, probably to the largest audience that I've ever spoken to. Even though I can't see you, I would like to welcome you all to this webinar. And looking at the people who've registered, I can see that you come from all over the world, even a couple of people from Australia. So, first of all, I must apologize that another webinar that I was going to present last month on energy efficiency obligation schemes, I was unable to present because I was ill at that time. That webinar has now been rescheduled to the 25th of June. That's in about 6 weeks' time at 2 o'clock Central European Time. And on the screen at the moment is the URL of the Leonardo Energy website that you can go to register for that rescheduled webinar. Don't worry if you can't copy that URL down at the moment, because you will be sent the slides, as Hans said, after this presentation. As Hans said, I was the operating agent for a particular DSM research project, and I just want to explain a little bit before I start on the actual presentation about the various organizations that I'm currently involved in. At the moment, I'm a senior advisor to the Regulatory Assistance Project, which is a global non-profit team of experts that focuses on the long-term economic and environmental sustainability of the power and natural gas sectors. RAP, as we are known, and the people who work for RAP are known as rappers, surprising as it may seem. RAP works in 4 regions around the world: in Europe, in the United States, in China, and in India. And I actually am working mainly in India at the moment, which is why there are some Indian characters. I'm working mainly in China at the moment, which is why there are some Chinese characters down the bottom of this particular slide. So that is RAP. I started working with RAP after I finished working with the IADSM program, but I'll explain a little bit about IADSM. IADSM is an international collaboration of 14 countries at the moment. The number of countries varies from time to time. At the moment it's 14, plus several international organizations, of which RAP and the Copper Alliance are 2. And we all work together to develop and promote opportunities for DSM. DSM offers solutions to problems such as load management, energy efficiency, strategic conservation, and related activities. And the work of IADSM program is organized through a series of research projects, which are known as tasks, and the results are reported in a number of publications. The DSM University is a slightly separate organization, but it's supported by Leonardo Energy and the European Copper Alliance, and it provides access in a structured way to the knowledge developed during the 20 years of experience in the IADSM program. And this webinar and other webinars in the series have been sponsored through DSM University, which also makes a lot more information easily available from the IADSM program. Now, to come to the particular project that I want to talk about today, this was a project on network-driven DSM, and it ran from 2004 to 2008, so it took 4 years of elapsed time, and 7 countries who are members of IADSM participated in the project. They were Australia, France, India, New Zealand, Spain, South Africa, and the United States. As you can see, it's rather a diverse list of countries, which made for interesting analysis and a collection of information about how DSM was practiced in those countries. The focus was on what I call network-driven DSM, which is concerned with reducing demand on electricity networks, otherwise known as grids, in specific ways in which maintain system reliability in the immediate term, and over the longer term defer the need for network augmentation. So basically, network-driven DSM is about two things: it's maintaining system reliability in the immediate term, and over the long term, it has a possibility to defer the need for network augmentation. This particular project was the first broad and systematic investigation of the potential for DSM to cost-effectively support electricity networks. Since this project was completed in 2008, there has been a lot of work done in this area, but this really was the first project, and it set out some of the original issues and did some of the original analysis about using DSM to support electricity networks. Now, in the project, we took a very broad church view of what DSM actually is. We basically included everything. Some definitions of DSM are quite narrow. We adopted a very broad one, and it included all those measures that are listed on the screen at the moment, which I don't intend to read out, but as you can see, basically we included everything that you could think of as being demand-side management. Now, this project identified and developed a wide range of DSM measures that can basically do two things in relation to networks. First of all, relieve constraints on electricity distribution and/or transmission networks at lower costs than building poles and wire solutions. So what we were really about was, okay, you've got a network which is constrained for whatever reason, it's reaching its capacity. Can we reduce those constraints more cheaply by using DSM measures than by the usual solution, which is to build more poles and wires? So that was one thing that the Network DSM project was about. The second thing was providing operational support services for electricity networks, achieving peak load reductions with various response times. Now, I'll be defining a little later on what I mean by operational support services, but these are basically support services that support the operation of electricity networks in differing time frames from a couple of seconds to maybe a couple of hours. Now, the project consisted of 5 linked investigations. So there were 5 fairly separate investigations that were done that were linked together to make the project as a whole. As you can see, there was a worldwide survey of network-driven DSM projects, an investigation of assessing and developing DSM measures, how to incorporate DSM measures into network planning, how to evaluate and acquire network-driven DSM resources, and finally the role of load control and smart metering in achieving network-related objectives. Now, the bottom line here is that this was a very large project. It took 4 years, and each of these 5 sub-projects or investigations were major projects in their own right. So in the 30 to 40 minutes that I've got today or tonight, depending on where you are, there's no way that I can go into any particular level of detail about the results of any of these investigations. So what I'm aiming to do is to explain simply what they did, to explain simply the main conclusions that they came to, and then at the end of this presentation, there's a page of URLs which will enable you to access more detailed information about what this project did, including links to individual reports on each of these 5 investigations and links to a couple of databases which contain a lot of detail about the DSM projects that we investigated in this particular project. So having said that, I'll start. What I'm going to do now is to look at each of these 5 investigations in turn and summarize what they did and what the main conclusions were. So the first one is the worldwide survey. Now, in this investigation, what we did is that we looked at 64 network-driven DSM projects from 13 different countries around the world. And we prepared pretty detailed case studies of how these projects were implemented and, as much as we could, what the results of the projects were. One of the things that I found difficult in carrying out this research was actually to find out what the results of projects were, because often that information was not easily accessible. But we managed to get useful information for 64 projects, which I think you'll agree is a fairly large number of projects. And it took a long time to do each of these case studies. So a lot of the 4 years of the project as a whole was spent on developing these case studies. The survey focused on projects carried out between the early 1990s and 2008, so roughly about a 15 to 18 year time period. And it focused on projects carried out in the 7 countries participating in the projects, but we also included projects from other countries, so that there were 13 countries altogether which projects were drawn from. The detailed case studies of the project were included in an online database, and that online database is still accessible, and at the end of this presentation there is a URL to that database. So if you want to look at those case studies, you can easily go to the database and have a look at 1 or 2 or all 64 if you want to. The case studies provide detailed information about ways in which the DSM measures can be used to relieve electricity network constraints and or to provide network operational support services. The 2 major conclusions from all that work in preparing those 64 case studies was that, first of all, you can use DSM to achieve load reductions on electricity networks, and they can be targeted, those load reductions can be targeted to relieve specific network constraints. And we had many examples of projects where this had been done. These days it's much more common to use DSM in that way, but when we started the project in 2004, not many people were actually using DSM in that way. Secondly, and this is where I explain what I mean by operational services, DSM options can also provide a range of operational services, including things like reactive supply and voltage control, regulation and frequency response, energy imbalances, spinning reserves, supplementary reserves, and generator imbalances. Using DSM in that way is still relatively uncommon, but it is being done, and it is being done quite successfully, particularly in the United States. And I see that use of DSM measures will increase as the years go on. Another important finding from the survey was that all types of DSM measures can be used to relieve network constraints and or provide network operational services. So all of that list of measures that I put up earlier can be used, though of course whether a particular measure is appropriate or cost-effective depends on what it is that you're trying to do. It depends on the specific nature of the network problem being addressed and the availability and relative costs of DSM resources in that situation. And again, the 64 case studies have examples of different ways in which DSM measures were used to deal with a range of particular network problems. So that's the worldwide survey. What I want to do now is to go on to the second investigation, which was assessment and development of DSM measures. What we did in this investigation was to look at the 64 case studies, and they were analyzed to identify the categories of DSM measures that can be used to achieve network-related objectives. We looked at the value propositions for each of these DSM measures and identified the specific network problems which each measure can successfully address. And in addition, we identified the success factors, the factors which result in particular network-driven DSM measures being successful in cost-effectively achieving network-related objectives, in other words, dealing with network problems. So what were the success factors? Now, I can't go into the success factors in any great detail, but I will draw some general conclusions. First of all, the investigation concluded that the value to stakeholders of a network-driven DSM project varies depending on the perspectives of the stakeholders involved. So depending on what particular type of stakeholder you are and what you're trying to get out of the DSM project, its value to you will vary. And the value can even vary among similar stakeholders. For example, customers located in network-constrained areas have a very high value from a DSM project that's directed to relieving those constraints compared with customers located outside those areas. The distribution of the benefits from network-driven DSM projects among many different stakeholders means that the project promoter, the person who is promoting and probably paying for the project, is unlikely to capture all the benefits. And this is one of the problems in relation to implementing projects of this type. The person who pays for it is not going to get the full value from the project because there are a large number of other stakeholders involved. Other parties who haven't contributed to the cost of implementing the project may well receive some of those benefits. To provide value to the project promoter, the total benefits from the project must be quite large, and the promoter must capture a significant portion of these benefits. And that provides something of a constraint in relation to the implementation of these projects. And it needs to be dealt with up front when you're contemplating a project. Who's going to pay for it and who's going to get the benefits from it? Now, this is the bit on success factors, which unfortunately I can't go into any great detail, but we did identify a number of external and internal factors that can contribute to the success of a network-driven DSM project. External success factors include government policies, regulatory regime, market structure, the actual degree of commitment by the project proponent, and that can vary, as I've mentioned earlier, depending on what the benefits are accruing to that particular person or organization. The technology that's available for the project, commercial considerations, and public relations benefits. Some projects are implemented largely because of the public relations benefits that the promoter gets from them, and that's a perfectly valid reason to implement a project, but it does affect how the project is actually implemented. Internal success factors, that is factors internal to the project itself, include things like project objectives, the target market for the project, the DSM measures actually used, market barriers addressed, outreach and marketing, the participation project, if it's a project process, if it's a project that includes a number of participants, and the customer service and delivery mechanism. So you can see there are a number of success factors involved in implementing a network-driven DSM project. The different network-driven DSM projects containing the same DSM measures, if there are 2 or 3 projects using energy efficiency, or using load shifting, or direct load control, or pricing initiatives, if they use the same DSM measure, they tend to have a common set of factors that contribute to the project's success. The challenge in designing a successful project is to clearly identify the success factors for each of the DSM measures included in the project, and to then concentrate on optimizing each of these factors. And that is pretty much a key to implementing a successful network-driven DSM project. So that's the end of the second investigation, and now we go into the third one, which is how to incorporate DSM into network planning. In this investigation, what we did was that we looked at the interaction between network-driven DSM measures and the electricity market structures and regulatory regimes in each of the 7 participating countries. And at the time we were doing this, there was some flux going on in relation to how electricity markets were structured and how regulatory regimes were implemented. So we had a bit of a fun trying to work out, well, what is actually being done in each of these countries here and now. And then the network planning processes implemented in each country were also identified and characterized, and that was also a fun time too, because trying to find out how network planning was done in each of these countries was interesting. And in some countries, they were not really sure within the country itself how network planning was done. It was a matter of finding the right people to talk to about that. Once we had done those two analyses, we then developed options for modifying the existing network planning processes so that DSM measures could be incorporated as alternatives to network augmentation. So instead of the standard method of building poles and wires, you could think about incorporating DSM measures to achieve what you were trying to do in relation to the network. Among the 7 participating countries, the planning processes for basically electricity transmission and distribution system varied significantly. And the variation occurs particularly in relation to the types and functions of the various organizations involved, the detailed planning processes and methodologies used, and the policy and regulatory regimes within which the network electricity businesses operate. And as I said, during the time we were doing this, some of those things were pretty much in flux. However, we did find that there's sufficient commonality to identify key areas where changes could be made to enable increased use of DSM resources as alternatives to network augmentation and to support electricity networks. We identified 3 key areas where changes could be made. First of all, in relation to forecasting future electricity demand. What we found at that time, and things have changed a little bit since then, but not very much, we found that forecasting methodologies frequently reduced global load forecasting by assuming a small amount of load reduction to take account of the potential contribution of DSM. And so when forecasters were doing the forecasting, they'd do their forecasting in the normal way, using various economic parameters about load growth and so on. And then they'd say, oh, well, somebody's doing DSM somewhere, we'll knock it down a little bit because of that. Our conclusion is that really, there are better ways of doing it than that. You can actually look at exactly what DSM is being done, make an estimate of what results of that DSM activity will be, and then incorporate that in the forecast. And that is increasingly being done these days, but at that time it was not being done very much at all. And I expect that in the future, a lot more sophisticated forecasting of the effect of DSM on load forecasts in the future will be used. The second area where changes could occur or should occur was in developing options for relieving network constraints. At that time, and probably pretty much most of the time now, the simple response to dealing with network constraints was how many poles and wires must we build and when must we build them by. Some network businesses, and surprisingly actually some in Australia, were leading edge in relation to this when we did the analysis, were actually providing information and formal opportunities for third parties with expertise in DSM to participate in the development of options that use DSM resources to relieve network constraints. And in fact, in the state of Australia, where I live, there is a formal process in place whereby if there is a proposal to augment an electricity network, then there has to be a formal process whereby people who have expertise in DSM are provided with information about what needs to happen, are invited to propose options for using DSM to relieve constraints rather than building poles and wires. And again, I think that sort of formal process will be used more in the future. The final area where changes could occur was in establishing policy and regulatory regimes for network planning. Government and regulators should change policy and regulatory regimes to reduce the disincentives faced by network businesses that use DSM resources to support electricity networks. Now, this has been a big issue for a long time, particularly in the United States, where regulators and governments at the state level in the US have implemented a whole range of different regulatory and policy mechanisms to make it easier for electricity businesses to implement DSM. And there is a very long history in the United States of how that is done, and there are a large range of different measures and policies and regulatory structures that have been developed to enable utilities to implement DSM. And some of those policy and regulatory mechanisms are now being implemented in other countries too. And really what we're saying here is there should be more of this. So that was the third investigation. We now come on to the fourth investigation, which is the evaluation and acquisition of DSM resources. In this investigation, there was a survey carried out of practices in the 7 participating countries to look at the processes that were used in those countries to evaluate, acquire, and implement DSM resources to provide support for electricity networks. Again, there was a wide range of processes employed, varying from almost nothing to fairly complex and detailed processes for actually evaluating, acquiring, and implementing DSM resources. Of the processes that had some content to them and were actually being implemented, they typically included 5 stages. First of all, assessing the need for DSM resources, and that is typically done in conjunction with an assessment of how many poles and wires do we need to build. So there are really 2 investigations that are going on: how many poles and wires, and can we do this by DSM measures, and if so, what DSM measures do we need and by when? Then, once you've identified the need, you then identify and evaluate the available DSM resources. Now, that can be done within the electricity business, or, as I said in the previous investigation, some electricity businesses were actually going out and asking people who have expertise in DSM measures what they could provide in relation to the need that's been identified. Then, if you haven't already contacted the potential providers of DSM resources, then you need to do that. Then you need to negotiate the provision of DSM resources, and finally acquire and implement the DSM resources. Now, in the report on this particular investigation, there are some examples of ways in which this is done. And I think that, there's some useful information there to anybody who's contemplating using measures to relieve network constraints or provide operational services. The best practices within each of those 5 stages are tailored to the nature of each DSM resource and to the specific purpose for which the resource is required. So it's really the first 2 stages that are crucial. First of all, you need to assess and identify the need. What exactly do we need in relation to DSM resources? And then identify and evaluate what's available out there. And if you can do those two stages successfully, then the rest of the process follows on fairly naturally and easily. So that's the 4th investigation, and we now move on to the 5th and last investigation, which is the role of load control and smart metering. Now, I must say that this is the investigation that has probably been superseded and overtaken in the 6 years since the project was completed, because there's now a whole lot of work being done on the role of load control and smart metering. But again, this was one of the first studies of of those particular topics carried out, and it still comes up with some conclusions which I think are still valid these days. Basically what we did was that we first of all carried out a survey of load control and smart metering technologies, looking at the functionalities and capabilities of load control and smart metering devices that can be used to achieve network-related objectives. And this is probably the part that is most out of date. What we did was we put into a database descriptions of 17 then available load control and smart metering technology products. Those 17 have now been hugely overtaken by many more devices that have been developed in the 6 years since 2008. So while that database is still available, it probably wouldn't tell you a great deal with the wide range of products that are available these days. Those projects that were in the 64 in the database were reviewed, and new case studies for additional projects were carried out to identify the factors that contribute to making such projects effective. And best practices in the use of load control and smart metering to achieve network-related objectives were identified. There are 3 ways were identified in which that technology can be used to support electricity networks. First, advanced meters, as is well known now, enable the implementation of time-varying prices, which sends price signals to customers that reflect the underlying cost of generating, transporting, and supplying electricity. And there have been many projects carried out on the use of smart metering and time-varying pricing for electricity, I must say, with somewhat varying results. These price-based response programs can reduce or shape customer demand, and I must say that they don't always work. Particularly, they can reduce peak loads on the electricity network and therefore reduce the amount of investment required in network infrastructure. Secondly, analyzing data from advanced meters provides end users with detailed information about the ways in which they use electricity, and they enable them to identify and implement energy costs and carbon saving. Again, since the end of this project that I'm talking about, there have been a whole lot more projects carried out in this area. Again, I must say, with somewhat varying results, even though there have been many claims about the effectiveness of using behavioral information in that way. I still think that the jury is out, and we still have to find the most effective way to use that sort of energy usage information to modify customer behavior. Thirdly, and I think this is the most promising part of the use of this particular technology, is using load control technologies to directly reduce peak loads on the electricity network by remotely switching appliances and equipment at customers' premises. Now, this is an interesting area which actually has a very long history. It has been used in Australia for over 50 years, where direct switching of off-peak water heaters was used to maintain electricity networks operational. And I well remember many years ago sitting in the control room of an electricity distributor in the northern New South Wales late at night and watching them switching banks of storage water heaters just to keep their electricity network running, which was grossly overloaded at the time. So this is a technology with a very long history, and these days a whole lot of new technology has been developed which enables much more sophisticated use of remote control and switching of loads. And I think it's the most effective mechanism for reducing peak loads because it requires only one set and forget decision by end use customers. You say to the customer, at what price level or at what level of energy use do you want your equipment or appliance switched off? They give one answer, and then it can be done automatically and remotely. And it is important to give the customer that choice, because if you don't give them the choice, they can see this as a sort of big brother operation, and oh, the electricity utility is going to come in and control my appliances, and I'm going to lose control. That's not what load control is about. It's about working with the customer to come up with a solution that is beneficial to both the customer and the electricity utility. Now, finally, we came up with some major conclusions from this particular investigation, which still stand today. First of all, interval metering is necessary to implement time-varying pricing. That's fairly obvious, and the only way you can implement time-varying pricing is by having interval metering. Secondly, and this is not well understood, interval metering is not necessary to carry out load control functions, despite what the meter manufacturers say. There is available technology at a much cheaper price than an interval meter that can remotely switch loads without requiring connection to a meter. And in fact, there are some devices that cost maybe a couple of dollars, a couple of American or Australian dollars, that can carry out remote switching of loads. So you don't need a very expensive interval meter simply to carry out load switching. Again, one-way communication, and not necessarily through a meter, is essential to carry out remote switching of loads. You need to be able to have some communication to the particular appliance or piece of equipment that you're switching. Two-way communication is not essential, but it is useful because it can provide valuable information to the program operator about the results of switching. If you have one-way communication, basically you send a signal down a wire or through the air by radio, and you don't know what the result is. Did it actually switch the piece of equipment or appliance off? If you have two-way communication, you get an answer back that says, yes, I did switch off, or no, I didn't. Finally, metering, obviously, in some form, is required for the settlement of the financial transactions associated with load control programs. And that's not any different from anything that happens these days. The only way you can work out how much electricity somebody's used and therefore how much money they owe is by having some form of metering. So those are the three investigations that were carried out as part of this big overall project. There's some general conclusions here. The overall project on network-driven DSM was the first broad and systematic investigation of the potential for DSM to cost-effectively support electricity networks. There have been significant advances since 2008 and the use of DSM to do this, and particularly in the technology that is now available. However, the main findings and conclusions from this project are still valid, and the project reports and case studies continue to be sources of useful information. On the final slide is information about how you can get access to all the detailed information that was produced in this particular project. So thank you very much, and I believe now it's time for Q&A.